Hi, everyone. So today's talk is going to be about HEIR hardware and benchmarking. And I'm going to divide this talk into the first couple of parts, seeing FHE from a technology consumer's perspective and what they look for and how do we want to benchmark. And then the second part is technology producer, that is us, compilers and hardware accelerator developers. And then we can talk about demos there. Okay, so we all know what FHE is, provides privacy at compute time, lots of privacy benefits, and some real world application that we think about is LLM inference, video captioning, spell check, DNA, and blurring. And there are also a lot of challenges to FHE, and we talk about technical challenges of performance, usability, and cryptographic expertise. But as we saw in the panel, there's also the problem of choice. There's a lot of FHE schemes. There's a lot of FHE hardware accelerators. And when someone wants to use FHE in the product, it's not always quite simple what or which technology, which software, which hardware they need to use for their application, even if their application is latency tolerant and accepting of the overhead that FHE provides. So we started this effort called FHE benchmarking. This is a joint effort under the auspices of homomorphicencryption.org. And so the FHE benchmarking is for technology consumer. Our goal is to have fully specified workloads, which provide some interesting useful use cases. And then you need performance numbers to inform deployment decisions and identify the trade-offs. And so the business should be able to make a decision which of my workloads could feasibly use FHE and which implementation and which hardware should I be using. And this encompasses a wide variety of things in FHE. So we've been working on this since last fall, and we kind of reached alignment on a few things. The first thing is these are the three kinds of user personas of our benchmark. Who are the consumers? Application developers who are interested in application level performance, FHE developers who are interested in scheme-based performance, and then hardware vendors who are interested in hardware performance. So we, as a benchmarking suite, we prioritize application developers the most, and then we kind of facilitate FHE compiler and hardware developers. The next thing we reached alignment on is what to measure. We measure what products care about. How much time is it going to take? How much space? It could be RAM, it could be disk space. How much network bandwidth? How much is the communication cost? What is the quality loss on precision? And what is the dollar cost of deploying FHE? So these are the primary metrics that we care about in our benchmarking suite. So the way that we started with benchmarking is, this is signature shy slide about FHE benchmarking suite and how we started developing it. First is to identify some use cases of interest, and then describe the workloads that facilitate that use case, and then collect them into some of our benchmarking suite. We have 10 plus workloads identified. All of them are in progress at varying degrees of completion. And we now have our first draft of FHE benchmarking suite that's out there, that's available to try. So the first two big workloads in the benchmarking suite are vector search. This is basically cosine similarity search. We think of use cases as biometric, match, RAG, and it returns entire matching workload. And we specify 3 different sizes for this benchmark. Small, which has 50K records, and medium, which is 1 million records, and large, which is 20 million records. And then the second one is ML inference. It currently supports a small MNIST model, and we have planned to add a CIFAR 10 and a ResNet 50, probably BERT, probably Llama 7b in the future. And we specify a model, its requirements, and then we also specify an acceptable accuracy. And it's available at fhebenchmarking.org, and each of these workloads have reference implementations. Not necessarily the fastest ones, but the reference implementations exist for clarity. So one big advantage of using the benchmarking suite is we measure a lot of things. And this is one of the measurements that the benchmark spits out when you run it. You can see that there's a server-side latency, there's a client-side bandwidth, there's key sizes that encrypted input, encrypted results. And also on the right side, we also measure quality, not both the model quality and also the encrypted model quality. So encrypted model quality is the first one, and the harness model quality is the plain text model. And all are invited to submit implementations. We are still working out many aspects of the suite, how to verify the submissions, how do we deal with non-open source implementations, and how we present the results. Examples of submissions will help us. And that's the link, right? So now I'm going to take a bit of a shift and talk about from a technology producer's perspective, which is how do we make FHE usable? And one of the biggest thing is having compilers. And HEIR is our compiler that we've been developing for a few years. And HEIR is built with the idea that it's a compiler toolchain with all of the established ideas in fully homomorphic encryption, and we accelerate research and lower the barrier to production. HEIR stands for Homomorphic Encryption Intermediate Representation. So we use MLIR to define dialects at varying degrees of stack that helps HEIR be a compiler. For example, given a TensorFlow model in plain text, HEIR can convert it into a model that works on ciphertext, and then it gets deployed on any of the hardware accelerators. So think of HEIR as a design environment. Some of the green ones are the newest features. But as you can see, there on the top level, there are the front ends like Python, TensorFlow, and then there are dialects, which are secret, which annotates whether an input is secret or not. And then there are scheme level dialects, there are library level dialects. There's also polynomial and modulus dialect that does all the math. And then there is the hardware accelerator. So the goal of HEIR is to support all parts of the FHE stack, all the way from front ends to hardware accelerators. And on the right side are some of the optimization techniques that exist that I'll talk about in a minute. So the number one requested feature was Python front end, and we have it. It is now supported in HEIR through the path of OpenFHE CPU. We have many new scheme and library support, both BGV, BFSDKKS from OpenFHE and LIGO. We have a lot of noise modeling techniques and parameter selection techniques. In practice, you can see that each of the lines is annotated with noise bound, and that's how you can track noise as you make decisions during the optimization pipelines. There's also ciphertext packing framework. We have a new layout annotation mechanism, which does many different types of packing techniques, and some of these are mentioned here. We also have many ciphertext management techniques like using ILP to do local and global optimizations, inserting renumerialization ops, modular switch ops, and scale management, etc. Another feature of the compiler is you have a debug handler that annotates your noise, that you can see the input and debug your code, because debugging in ciphertext world is messy since everything is encrypted and you see a bunch of gibberish. So having this call which debugs things and adds noise is also one of the features in HEIR. There's also a new polynomial approximation solver. Carat Theodory FAIR is the best way that we have found the most efficient one. There is general polynomial evaluation. There is Peterson, Stockmeyer, baby step, giant step, and Chebyshev basis support. And we are continuously working to integrate with more and more ML frontend like PyTorch, TensorFlow, etc. And not only that, there's low-level dialects like polynomial dialect and modulus dialect and RNS dialect that I think will map towards hardware exit dialects. And our plan is to lower FHE scheme dialects all the way to polynomial level. Coming to the interesting part, the hardware. So far, we have integrated with Belfort FPGA, as Michael has mentioned. We have a basic baseline pipeline running that you can compile to FPGAs from HEIR and run on FPGA. We also have integrated with Optalis's C API. We have integration with TPU through JackSite API, which allows you to run programs on TPUs or GPUs. And we have many more planned. Okay, so now coming to the real hardware accelerators. The first one that I'm going to show is TPU. In TPU, we're going to go through secret dialect, LWE, CGGI, JackSite, and TPU, and we use YOSIS and arithmetic, YOSIS optimizations, batching, and arithmetization. So I'm going to share my screen. If you have attended Stanford Summit, these are the same demos. So the first one is running a single AND gate. So the client and server key alert from a file. So it takes 8 milliseconds to run a single AND gate. So the second example that I'm going to show is add1, which has a bunch of lookup table lat3s, which are bootstraps. And so, so the first one will run a sequential, and the second, and then it will immediately run a parallel version. So if you see when it's running, for a single one, all of the lookup tables are sequential, and for a parallel one, they will be batched into one lat3, so it will be the execution time of 3 lat3s. And you can see that it's 19 milliseconds for the first one, whereas only the 30 milliseconds for the second one. Okay. And the next thing that we have planned for TPU is custom kernels, multi-host scheduling, and custom entity kernels. We also have Belfort FPGA integration that Wouter is going to talk more about. Wouter, you may be muted.
Hello, do you now hear it? Yes, I see it. So we have integrated the Belfort FPGA into HEIR as well. I'm first going to share it. Yes. Oh boy. And to do that, it is actually now possible to implement a program in HEIR, let it compile completely down into parallel executable code. A multi-FPGA is supported through the HEIR framework as well, so you can just basically give it a neural network in HEIR. We can completely compile that down into Belfort-ready code, and that can be scheduled across a multiple of CPUs. And one of these, another demo that we have developed that is also possible to run on the Belfort FPGAs is the demo that Michiel also has called out in the beginning of the session, which is called the Leuvenstein demo. And in this Leuvenstein demo, we will look at the added distance calculation between two strings. And in the added distance calculations, we'll basically check how similar two strings are. And this similarity we will do by counting the number of operations to convert the first string into the second string. For instance, it's how many deletions, insertions of characters do we need, how many substitution of characters do we need, and so we can actually check the similarity of two strings. The demo that I will show you today is also available on the Belfort Labs GitHub, so if you want to play with it, please check it out. In this demo, we actually have built up a database. And in this database consists of 48 names. And now it is possible to query if a name is present in the database or not. This is done fully in the homomorphic domain. And because we use this added distance as a basic, we actually don't need to exactly write our name. One of my co-authors of this work is Jan-Pieter Danvers. Very nice guy, but the guy has a very terrible name to write down. So, for instance, when we talk to him at the conference and we actually understand Jan-Peter Danvers, something like that, but we still want to check it in our database. And now this query is run against all of the names that are encrypted in our database. And we compute the edit distance for each of these individual names. Once this computation is done, we will decrypt our outcome, and we will use an inference algorithm to actually match our name against one of the encrypted names. By the way, this is now running in CPU environment. So now all of our computations are run at a normal CPU implementation. What we now can see is that our very wrongly written name is matched with the correct writing of the name, namely Jan-Peter Danvers. Very nice with all of the special characters as well. But of course, we now can also run this demo on the Belfort FPGAs. With the exact same name, you can see that already that this computation is way faster. Our CPU implementations roughly take 40 seconds to calculate, while our FPGA implementations takes only 10 seconds. Besides that, there is actually also another demo build that has Michiel talked about, which is called the AES transciphering. And in this AES transciphering, we will first encrypt a number using this AES transcipher, using AES encryption. And this AES encrypted number is then converted into the TFHE space, and then we can operate an operation in the TFHE space. As well, this demo is also available for you to try in the GitHub repo of Belfort. So, sadly enough, we first need to recompile the demo. This is actually a demo that is made by Baron, that did a joint internship between Belfort and the KU Leuven, and she fully implemented the AES transciphering in the homomorphic domain, and also did the exercise of actually mapping this AES transciphering, because there is a lot of existing work, to existing FPGA implementations. That is also possible. Yes. So sadly enough, now we still need to wait a bit for the code to compile. I could not pre-compile this code. But believe me, the demo will be worth it.
The interesting thing about this demo is that it kind of AES transciphering, so it's easily integratable with HTTPS, SSL, and any of the storage mechanisms usually use AES. That's kind of exciting.
So voila, here is our demo. It is now possible we will do a very simple addition. So for instance, we will take the magic number 32, and we will add that to the number 31. What now first will happen is an AES key will be generated and will be used to encrypt these numbers. This number, these AES encryptions are now sent towards the server side, which we already can save like almost 99% of memory bandwidth. These are then converted into the FHE domain. For this 2 ciphertext, this takes roughly 6.6 seconds. Once these in the ciphertext domain, we can calculate them very quickly. We can do this addition very quickly in the AES domain, and then this result can be sent back to our client side, which can decrypt and actually see that our expected number is the correct outcome. So that was it for our demos. And now Shruthi will tell you what's up next with the whole project. So Shruthi.
Next slide. So what's next for HEIR? I think our primary focus is support encrypted inference and support hardware acceleration integrations as much as possible, and support the research goals of the community. And to that effect, the first next slide is the demos that I've run are open source, so there you can try them at the GitHub repo, Google/Fully Homomorphic Encryption. These are more and more demos will be added to this page, but to begin with, we have a couple of small demos. Please try them out. If you run into issues, please file GitHub issues. Next slide. And we also have the HEIR plus Cloud FPGA demos. They're also at Google/Fully Homomorphic Encryption repo, and both Leuven and AES transciphering is part of the demo suite that you can run. Next slide. And as I said, our primary goal now is encrypted inference, get a lot more kernel support, define our input dialect, support more front-ends such as Torch, TensorFlow, support a wider variety of architectures, and then get encrypted inference through to prod. Next slide. And our bigger goal is supporting the research goals of our community. Next slide. We collaborate with a lot of universities. We have presence in FHE.org, WAC, and through student researcher programs, through visiting researcher programs, through partnerships, to cybersecurity programs. I think we grow as a community together. Please reach out if there are opportunities that show up. Next slide. Thank you. HEIR.dev is our HEIR repo. Google/Fully Homomorphic Encryption has all the cloud demos, and FHEbenchmarking.org has the benchmarking suite that I presented earlier. Thank you, and we have a bit of time for questions.
Great, thank you very much, Wouter, Shruthi. That was really interesting. So there are some questions. I can see Jeremy's been busy in the chat as well, answering some of them, which is great. But I'll go to the unanswered one first from Todd. So how does an AI vendor protect itself against model stealing with encrypted inferences?
I think the way that we have structured the current models is that the model is public to the server, but how does an vendor support it? I think there are ways to hide the model by the weights of the model, but hiding the architecture is still an interesting and open question for ML models, simply because the model also kind of shows off a lot of data.
Okay, great. The user interface for the demos is really nice, by the way. I just wanted to say that. It kind of gives an interesting vibe. So that's cool. Any other questions from the audience? Or perhaps if anyone else, either of you has something else to say about Nandini's question, which was, does the TPU have native modular arithmetic support?
No, two TPUs are supported for low precision floating point arithmetic, whereas we know FHE needs high precision integer arithmetic. So TPU has the concept of bfloat16, where it kind of tries to divide the 32-bit integer multiplication into 8 bits and tries to put them back together. So that's one of the reasons we need to develop different and more specific kernels for TPU to improve arithmetic. And even with modular arithmetic, we have to come up with special kernels. And Jian Ming, one of our student researchers, is actually working on this. It's part of our JAX-site repository if anyone wants to check out. And there's a paper, cross paper, and that's the right one that's in the chat.
Nice. Okay, there's two more questions. So the first one, any plans for TEE on TPUs?
There's TEEs being planned for CPUs and GPUs. I think they're out. TPUs is an interesting question. No update from me on that part, but that does an interplay between using TEEs on TPU and FHE on TPU is an interesting question to think about.
Yeah, And one more from Mutu. What is your take on the HPU from Zama, which I guess was the previous talk?
My take is, how can we get this integrated to HEIR compiler and see how it performs? I feel like the benchmarking suite was what I'm going to rely on, because there's almost 3 different FPGAs presented today, and understanding the trade-offs between all of them is a question mark still. My take is, it's awesome that there are so many FPGAs, and we understand, we grow more as a field as we do different kind of optimizations and combine them together as a whole.
Yeah, nice. Yeah, it's been really nice to see some different approaches. I agree with that. Okay, any more questions from the audience? If not, Wouter, Shruthi, thank you very much.